this is some detour, and I told you previous time the reason I did it in course is because it is basically a requirement for the course to include electromagnetism. So the students should know it, because that is how the course should be. But you don't need it to understand general relativity. It's really a sidetrack. B0 plus A1 B1 plus A2 B2 plus A3 B3. And now minus 1, that is equal to I squared. So you could also write this as I A0, I B0, and then here the same.
Oh, okay.
So you could also take normal factors and put an I in the 0 component and define them in this way. That is how I learned relativity.
That's very interesting.
But most people don't do that. Here exactly much more the invariance is clear. That here you see immediately that the indices are the same, so this expression is invariant on the Lorentz transformations. Right. That is why you write it. You want to see the invariance, because in physics, all laws of physics should be invariant on the Lorentz transformations.
All right.
And that's why we have that.
Okay, so that's a big thing for me, but really the biggest thing, he starts to get into the derivation of the Euler-Lagrange equation in detail, starting on this page. I suppose I should probably zoom in instead.
That is in one dimension.
Right.
Yeah, so he does a variation, he actually does more dimensions, it makes it a little more complicated. Yeah, so you want me to derive it?
That would be it. That would be definitely interesting. I would like to see a derivation of the Lagrange equation again. Probably write it down this time.
The Euler-Lagrange equation.
Mm-hmm.
So we start with an action. It's an integral over a Lagrange, which is a function of L Q dot, and in principle also the time, but we take it time independent. And this actually can depend on the time. And what this is really is a functional. It depends on Q and Q dot, or maybe on Q only. So this is something that depends on what Q of t is. Mm-hmm. For each Q of t, you get a different number. So you can calculate that. For example, what it can be is that L would be 1/2 times dq dt squared. And you integrate between 2 points, t0 and t1.
Mm-hmm.
So if you have a function, q of t, like that, so it's q of t versus t, and then you calculate the slope, square it at every point, just do the Riemann sum, and you know the Riemann sum,
Mm-hmm.
and just calculate the slope at each point, add it, and then that is the action.
I see. So.
And then you like to minimize this.
Right.
So maybe
something a little similar right here, with the kinetic energy.
Yeah. Let me do it a little bit more intuitive. Just a Riemann sum, and I try to minimize the slope. So how can I make the square of the slope as small as possible?
So you mean I can vary the where I take the Riemann sum?
Yeah. I'm looking for a function so that the slope becomes as small as possible, the square of the slope.
And what am I allowed to vary to?
Oh, this function, you can look at this function like this. You look the slope at every point, and you try to make it as small as possible. And so there's a square here. So that means this is always positive. And how small can you make it if it's always positive?
0?
Exactly. It cannot get smaller than 0. So what is the...
Right, just the constant graph.
That would indeed work if q of t0 is q of t1. That would minimize the slope squared. But this is not really very interesting. This just means that q is the coordinate. You stay on the same place. Nothing is going on.
So
now you could look at when this is not equal to 0. So if you have a picture, so here's t0, here there's t1, and so you look at q of t0 here.
So for what graph that is not constant is the derivative, and by extension the derivative squared, equal to 0?
It is never equal to 0
Right.
because the endpoint has to be here. So this is q of t1. So 0 cannot be the answer. So the question is, what can it be?
We have to minimize it.
You have to minimize it, so if you, for example, if you start with a straight line, because that's like, and then you look.
I'm not sure we can minimize anything if we're looking at a straight line because
Yeah, no, I know, but you have to say, now I'm going to deform it a little bit. I'm going to minimize each segment, and now I deform it a little bit. And I see here the slope becomes larger and here it becomes smaller.
So it works out overall?
Yeah, but you also know that you square. And if you square a number, it actually gets bigger. The bigger wins if you square it. For example, if you calculate the average of 3 plus 1 divided by 2, and the average would be 4. But if you do the squares, 1/2 9 plus 1, that is equal. So in this case, if you square it, and I would compare this to a constant slope, so this term is going to be more important. So what you would think is that this would be the solution. That this the straight line minimizes.
I'm sure that can't be a rational solution because there were very little systems where it's just a straight line, just an object moving at constant velocity.
No, there are many. I think I might just throw this. This moves at constant velocity to first approximation. If you drive in a car and there's no traffic, you also move at more or less constant velocity.
That's true.
So indeed, that's a solution, constant velocity. But you would like to prove it better. And the way you do that is, as I said, you change, you have q of t as a function, and you change that a little bit. Q of t plus a little bit, delta q of t. So this is the function q of t, and this is my delta q. It can also be a function like this, which is slightly different.
So you're trying to prove that by setting delta Q to 0, do you minimize Q? Or delta to 0?
No, I'm going to find the Q of t that minimizes this.
Right.
And I'm going to show that by looking at close to this so what I know is so what I'm going to look at the action, and when you're at the minimum, what always happens, so if you have a normal function, say this function, where's the minimum?
Right there at the vertex?
Yeah, but at the minimum the slope is equal to 0.
Mm-hmm.
That happens always at the minimum, also in this case. So I actually look at the slope. The minimum means that the first order correction, so at this point, if I do a Taylor expansion, it is a constant plus alpha times x squared, where x is at this distance.
Right.
Because the linear term vanishes at this point. And that's what I also do here. So I'm going to find the extremum, which, and you do that by just calculating.
Where the derivative is 0, right?
Yeah.
So this is...
Technically, this is a functional derivative. So s plus delta s. So I count delta s. So I do the change in this. So that's the integral from t0 to t1, L q plus delta q. I have to erase my picture. And here is q dot plus delta q dot. And dt. So this is small. So then the derivative also should be small. That's not necessarily true, but typically when the function is small, also its derivative is small.
So we're assuming that the function is well behaved, right?
No, not really. Should be reasonably well behaved. But we integrate it, so a few singular point doesn't matter that much. And now we can Taylor expand it. So the first term, when this is equal to 0, is just, if I do s plus delta x, is just the action we had before. That is L q, q dot dt. That is the first order term. Mm-hmm. And then we have the second order term. That is, I don't have space here. So the second order term is so I have to Taylor expand that. So I have here the integral over dt between t0 and t1 dl dq. So I differentiate with respect to q times delta q plus dl dq dot times delta q dot, and q dot is this is the derivative ddt of delta q. This is what I get. And now I want, so this is delta s. And now I want to find the minimum. That is when this doesn't change to first order. And now you see, this is actually the derivative of q. And this is delta q. And we want to have the same thing. And you can actually do that by integrating by parts. So this is dl dq times delta q. And then by integrating by parts, this term you get ddt times dl dq dot times delta q. And you also get boundary terms.
Right, so...
The boundary terms are dl dq dot times delta q between t0 and t1. So this is just plain old-fashioned integration by parts. Now, if I have again here my trajectory here, so that is q of t versus t, I now require that at t0, and this is t1, that delta q actually vanishes at these points. So I minimize subject to, so delta q of t0 is equal to 0, and delta q of t1 is equal to 0. And you have to do that, otherwise you have this boundary term. So we choose that such that this term becomes equal to 0. And now you see the equation what we have, because this is an integral, and there's an integral over dt. It should vanish no matter what change I make in here. It should be 0. And that can only be if the coefficient is equal to 0. Maybe that's the most complicated thing. So from this, we find that dl dq minus ddt times dl dq dot, that is equal to 0.
I just wanted to ask, can you show that integration by parts for a second?
Yeah, sure, you always should ask questions. And I can do that. So we had this expression, so that is integral from t0 to t1 times dl dq naught times d dt of delta q times dt. And with integration by parts, what you do is you first of all take the primitive of this and the derivative of that with a minus sign. So that's integral over dt from t0 to t1. The derivative of this ddt times dl dq dot times delta q. So that's one term. I take the primitive of this and the derivative of that, and with the minus sign. And the boundary term, what you do is you leave this term, so you get dl dq dot, and you take the primitive of this one, delta q, and you evaluate it between the two endpoints of the integration. Maybe you learned integration by parts in a slightly different way.
Right, yeah. So now I was taught integration by parts. Can I have it for a second? Alright, so for example, if you have, I don't know, something like this, we are just taught to denote one as u and the other one as dv, or where u and v are just some functions of x, and it's said to be equal to u times v, which is essentially just the indefinite integral of dv, minus the integral of v, which is that, du, which would just be 1. Now, of course, this, the integral of sine x dx would be minus cosine x, and so you would plug that in here, and this would be x. And so you'd just be given this and the integral of cosine x dx.
Yeah,
Right.
yeah, this is the same. And
So what would you designate?
oh, well, yeah, I don't designate.
Right.
So
Okay.
it's simple not to do that. And so what you do is this is the primitive. So in this case, this would be the dv. In fact, the ddt of v, and this would be the u. So this would be the u. If you want, you could scrap these two. Then it really becomes integral over dv.
Ah, I see.
And then one term was, the first term you got was the boundary term. That is when you integrate, that is u times v, and maybe you do it in a different way. So if you have u dv, you can write that as d uv minus v du, using the product rule. That is what you are using. And if you integrate this, this becomes an exact integral, because there's a d here. You have to evaluate it by the endpoints, and here you have the minus sign, and now you have the derivative of du, that is this. That's the derivative of du, and the v is now without the derivative. So it's exactly the same.
I see. All right. Thank you for clearing that up. I understand that a little better now. So one other thing I wanted to ask about.
Now you want to find the solution still.
Oh,
Okay,
right.
so the solution of this equation. So we looked at this problem. There was q of t0 was here, q of t0, and q of t1 is here. And we want to solve that for the action now is equal to 1/2 q dot squared. There's no term here because there's no q dependence. And here you get minus ddt times dl dq dot is q dot is equal to 0. And that means that q dot is constant. Say alpha, and that means that q is say beta plus alpha times t. So indeed, you get the solution which we thought it would be. This is the solution.
Wow.
And the alpha and beta are determined by the values here. So you can also do that. Q t0 is beta plus alpha t0. Q t1 is beta plus alpha t1. So alpha is equal to q t1 minus q t0 divided by t1 minus t0. You subtract that, and then if you substitute that, you find beta.
Seems simple enough.
Yeah. So yeah, we find the correct motion, and you know it should be the correct motion because there's only kinetic energy.
Oh, right. That's why it's a straight line. So because we're only considering kinetic energy.
Yeah, there's no potential, so a particle is moving at constant velocity forever. It's like a rock in the universe with nothing in it. So the next thing is, next question.
Right.